Okay, because of the time limit. Okay, so now you know a little bit about black body radiation. Oh. So now let's go back to our empty box. I apologize, I have a runny nose. I have to do something about it. So you now understand this curve and this equation and this equation. So we can control the amount of radiation inside of an empty box by changing the temperature of the walls of the box, but we can't get to T equals 0. It just takes, it's like trying to exceed the speed of light. You just can't do that. So we can reduce the temperature, which reduces the energy according to this formula, sigma T to the fourth. And now here comes an interesting problem. How many people have or are taking differential equations? Okay, so one of the features of when you're doing differential equations, you have to set boundary conditions. Let me give you an example of a boundary condition. Here's a guitar. Strings. One boundary condition for guitar string modes is that this string is bound here and here. This tuning engine holds the string. So you cannot have, you can have this kind of string mode, but you can't have one that does that. The string has to terminate at these 2 points. That's in differential equations. That's called a boundary condition. The same thing applies for the waves. Remember we said that the box is empty of matter, but it has radiation in it. The same kind of thing is true here. The electric field, which you'll learn about when you take physics or if you're next spring, right? E&M. The electric field has to be 0 at the walls. That's a boundary condition, just like in this case of a guitar, violin, or other musical instruments. So the wavelengths can't be any old wavelengths. They have to fit in the box. You can't have a wave in the box that does that, where it doesn't complete a wave here on this wall. So, so let me repeat this one. A higher frequency wave has to terminate here and here. A higher frequency wave in here has to terminate at here and here. So we have this boundary condition. We can't ignore that. So we can't have really long wavelengths in the box. If the box, say, is a meter on the side, you can't have a 3-meter wave fit in there. And if you study black body radiation in university life, you'll see why that's a mathematical technique for determining that. So what is the longest wavelength we can fit in the box? Well, here's what the Wien displacement law comes in handy. It tells us the longest wavelength that a black body curve can have. So we'll keep that in mind. So we'll repeat here. This is what I just drew on the board. Here's the dotted line is the Wien displacement law going from 6,000 Kelvin, kind of like the temperature of the sun, 5,000 for 3,000. Many stars have low temperatures, and their peak of their curve is out here at 3 microns. Right? Remember, when you do this, units have to be in microns and kelvins. Okay, so now we introduce something else, and that's the Heisenberg uncertainty principle. And what this says is, there's many ways to say it, but this says, if I measure a space, let's say the interior of the box that we've been talking about, if I measure it for an extremely long time, a short time, very short time, the range of energies that might be detected in the box can be very large as long as this product is about equal to or greater than Planck's constant, which has, in these units, has a number 10 to the minus 34. That's a tiny, tiny number. But we now know this is true for atomic particles, subatomic particles. This is a foundational rule of quantum mechanics, that the product of the uncertainty in temperature, in energy, and the uncertainty in time of your measurement has to exceed this number. So if you want to have a long, let's say you want to sample the energy in the box for 1 second, this range of energies has to be extremely small so that this times 1 is still bigger than this. Okay? There's other features to this as well. I can mention one right now. We have a couple of minutes. So let's talk about a different interpretation of Heisenberg's uncertainty principle. And this one goes like this.
And just to clarify, by sample you mean observe, right?
Observe, right.
Measuring.
Right. We could
the amount of time of your measurement.
That's right. We could do this. Let's go back to the box. We could put what's called a radiometer in the box and measure the properties of the radiation in the box. And if we do that for a period of time, say 10 to the minus 19 seconds, we would find an uncertainty in the energy in the box on a scale of a joule. So this is in joule seconds. Energy is joules. Time is in seconds. For those who haven't had physics yet, you'll get plenty of that. Another way to express this is if you measure momentum, the uncertainty in a momentum measurement, and the uncertainty in position measurement. These are called complementary parameters. The product is always got to be approximately equal to or greater than Planck's constant. You can derive this from that or vice versa. Okay. Oh, and so what this says is, if we go into this mythical box that we're talking about and measure, and we measure the energy level in the box for extremely short times, we could find high energy particles in the box. You can't look at it very long because the particles appear and disappear. They're called virtual particles. So let me remind you of something. I don't know if you remember this, but last week we talked about the Planck scale, and we talked about the Planck time. So the Planck time is like 10 to the minus 43 seconds, right? 2 times 10 to the minus 43. So let's say we went and built a radiometer that went in the box. And it has to be a cold radiometer. Remember, we can't have anything warm in there. We want the lowest possible temperature. And we measure for 10 to the minus 43 seconds. So, time to do a little more math. So we have 10 to the minus 19. All right, let's do it this way. 10 to the minus 43. That means approximately. So what number do we get if we make this?
10 to the minus 34, right?
You get
10 to the minus 19.
Sorry. What number do we, thank you. What number do we get for the uncertainty in the energy?
9.
We get 10 to the 9th joules. That's the uncertainty in energy if we measure for this very, very short interval of time. This is the Planck time, T sub P. What is this equal to? You remember? This is the Planck energy. So, what is the Planck, and remember I told you what the Planck energy refers to. If you squeeze the Planck mass into a Planck volume, what do you get? You get the smallest definable black hole. So what this says is if we measure in our empty box 10 to the minus 43 seconds, 10 to the minus 43 seconds, we'll be looking at a black hole. And so that's another way. I didn't mention it last week because we didn't have all the concepts, but that's another way to think about why the Planck scale is limited. Because if you try to go into an empty box and measure for an extremely short time, the only energy you will see is something that's akin to a tiny black hole that evaporates right away, and you can't have anything smaller than that. That's the smallest increment of stuff.
So you're saying black holes are appearing and disappearing right now?
Right. In this room, right now, if you measure on a time scale close to the Planck time, there's black holes appearing in, that's what this is supposed to represent. This is called quantum foam.
There's like 10 to the 43 black holes every second.
They're all, it depends on how fast you want to measure. There's every kind of particle imaginable in this room. We already know it's got a lot of nitrogen and oxygen, that's what we're breathing. But if you could have a vacuum pump and pump it out, make that special little box we've been talking about that's empty of matter, and then you looked very quickly and carefully, you would see every conceivable kind of particle and every conceivable kind of light. But remember, the light has to fit in the box. Boundary, I'll remind you of the term, boundary conditions. So we're getting...
Did his math work? I mean, there's 10 to the 43 appearing every second. Is that math?
Why not?
Well, I don't know.
If you take a second of time and measure 10 to the 43rd times, each measurement is 10 to the minus 43 seconds, you have a probability. Now remember, this is not certainty, this is the uncertainty. But there's a possibility, every time you make a measurement, there'd be a little microscopic black hole in the box. Okay, so let's keep that in mind. So quantum foam is implied by the Heisenberg uncertainty principle. And we've already agreed there's energy in the box. We can't get rid of all of it because of the temperature of the walls. We've already said these things. Virtual particles of every type will be in the box. So remember, the title of this talk is nothing, but there's actually, you can't have nothing. It's just churning and boiling constantly. This was a big dilemma back in the 1950s when people were working hard to understand how does an electron have an electric field? Some of you, except for Diego, you haven't seen this yet in physics. Here's an electron, and around it is an electric field. This is a vector. But that means the electron is in an electric field that it makes, and trying to take into account how it interacts with itself created all kinds of mathematical problems and how to get rid of infinities that filled the mathematics. So this is all fundamental stuff. High energies for short times. Okay, now we come finally to the nexus of what we're talking about. Casimir, 1948, a Dutch scientist, he realized there's an interesting experiment we could do to study a box filled with nothing. And he asserted that if we put two plates in the box and put them extremely close together, there will be a force between the plates, and here's why. I'll explain it. Here are the two plates. Remember I said we have boundary conditions. So the box has electromagnetic radiation in it, but here we have these two plates, and unless the wavelengths can fit between the two plates, they cannot physically exist. That's a result of the boundary conditions related to electromagnetic waves. So he said the box, now I didn't draw the box here, but it's around these two plates. He said the whole space is filled with virtual particles, and they're bombarding the plates every way they can, except between the plates, the particles or waves, electromagnetic waves, that are bigger than this space, they can't fit in there. So in here we have less energetic activity than we do out here or over here. And it's like, you've all done this. If we took a ride right now up to where I used to live at 9,000 feet and opened the lid, so now we have air at a 9,000 foot pressure altitude, and we drove back down here, the bottle would get crushed. Because you have more on the outside than you have on the inside. You don't have balanced forces. So Casimir says, I propose if we build this experiment with the plates extremely close together, we can actually measure the vacuum energy in an empty box. And that was 1948. It took until, I think, the late 80s, and the experiment was eventually done using modern electronic techniques. There's another part to this that you don't know unless you've taken quantum mechanics, and that is the particles, the virtual particles that can appear in a vacuum they have a wavelength too, related to their quantum mechanical behavior. They're excluded from here if their wavelength is bigger than this space. So what we have is a foam of photons and particles out here and out here, but fewer in that space. Now, this is where Mr. Hanklin might have to leave the room. So we can estimate the pressure that will be measured if we build this experiment, and we are going to call the distance between the plates L. And what are the parameters that relate to this experiment?
Temperature.
Could be. Turns out, if you do the arithmetic, temperature doesn't have an effect. Speed of light, it's a quantum mechanical thing, so Planck's constant, the space between the plates. And now, what is the relationship between these parameters and the pressure? Late 1990s, this was measured. So we use a technique called dimensional analysis. Planck's constant has these units: speed of light does distance over time, you all know that. Length has the units of length. And pressure is represented as force per unit area. I'm not going to go into any detail here about this, but it's relatively easy. You can see what I'm doing here, a little bit of algebra, and we get this relationship, that the force per unit area, also called the pressure, for an experiment like this is Planck's constant times the speed of light divided by the separation of the plates to the fourth power. So very interesting, we get that fourth power effect again. Now, let's see what happened. And what this says off the bottom, we are going to do dimensional analysis later in the semester so you can see lots more examples. Here's the actual computation that Casimir did. It's pretty complicated. I'll show you some key equations here. You got to be able to do this integral. It's a doable integral, but it turns into, the result is a infinite series. Sum over a parameter n, where n is raised to the 3 minus s power. What is s? Well, you can see, here's s. The energy per unit area depends on s. And so we're interested in this summation. This is called the Riemann zeta function. It describes this sum, and it has this general property. Riemann zeta function says, I'm going to sum from 1 to infinity, so this implies a power series. I'll show you in detail here. So if s is equal to minus 1, this becomes a sum, 1 plus 2 plus 3 plus 4, and so forth. And for the zeta function for minus 3, looks like this. We sum an infinite sum where every term gets cubed. So for n equal 1, we cube 1, we get 1. For n equal 2, we get 2. Cubed is equal to 8. 3, 27, 4, 64. So we get a summation of cubes, and it can be shown rigorously that this is equal to, any guesses? What?
12.
It's not 1/12.
Well,
Because
120. Right? Yeah.
1 over 120. And this is why I want Mr. Hanklin to leave. And this is a formalized version of an infinite sum, but it's critical, and here's what's really intriguing. Here's the actual result. Remember on the prior page, I got HC over L to the fourth. Here the dimension is A. Easy to see that. Here's the actual result. HC over 240 and then pi squared. That's what you get if you use this formalism. And now we have a chance to do an experimental confirmation. If Casimir's theory is correct, he gets this. If it's correct, we should measure this pressure in the experiment that was done in the late 90s. And indeed we do. The only way you get the right answer is if you are willing to accept that the sum of the cubes is equal to 1 over 120.
Okay, but your dimensional analysis left you off by more than a factor, by more than an order of magnitude.
Yes, dimensional analysis, yeah. So
Yeah.
Mr. Hanklin is
So
correct.
Physicists are happy if they're within an order of magnitude.
This is this, here's what this does tell you.
I'm an engineer, just saying.
If, this is what this tells you, this is a scaling law. It tells me if I double the size of the spacing, the pressure goes down by 2 to the 4th. That's what we mean by scaling law. The numerical factor here, the pi squared and the 240, is of less interest if you're in the laboratory and you say, how close do I have to make the plates so I can see this effect? So what have we learned? Well, everybody got a little introduction to Planck's function for the black body, Stefan Boltzmann equation, the sigma t to the 4th, the Wien displacement law, Heisenberg uncertainty principle, we got a chance to refresh on that, existence of particles and waves that are virtual, that appear and disappear on a scale of time of 10 to the minus 30 seconds or something that, and we learned about the Casimir effect. And interesting, here's once again the Riemann zeta function. If you put a -3, you get 120, but it's also true for the same function, if you put n equals -1, you get minus 112.
If you put a -2, don't you get 0?
You do, and there's an explanation for that. This is a well-studied, and Riemann zeta function has been thoroughly studied.
Oh, wait, go back. On the 120, one more. You said that that's been confirmed, but really, have we actually confirmed the constant there, or have we just confirmed the scaling?
No, this is the actual absolute value of the pressure measured in an experiment. If you measure that,
we've actually measured h pi squared over 240.
right,
Okay.
and it's been confirmed that the pressure varies as a
That is
to the
a
fourth. So I don't want to draw too much attention to this, except to say it leans in the direction of believing. Or I'm not trying to prove math by doing the Casimir experiment. It's much more important to know that Casimir's analysis of what goes on inside of a vacuum can be described by this analysis, which is repeated here. And we actually understand that an empty space is surging with activity. And the Casimir effect demonstrates it. Okay? So I think that's the end. I had this.
What would it be if the Casimir effect was incorrect? Instead of a to the 4th, what would you expect?
Well, dimensional analysis says you must get L to the 4th. Next year, I'll present this and I'll change the notation so it matches the. This, you cannot avoid this unless you pick the wrong parameters to describe the physics.
I mean, you can think of it as the two plates are being attracted by. I just lost the term for it.
Not electrostatic.
Yeah, electrostatic forces.
You could assert that.
Why can't I remember
The Coulomb forces.
Yeah.
You could come up with a different theory.
Which would go as r squared.
Would go as r squared, except we've agreed that we've pumped out the thing, there's no electrons, except virtual
There's
electrons.
no electrons in the plates.
There are electrons in the
And
plates, but
they've got to be conductors, right?
no.
Well, to meet your boundary conditions of an electric field is 0.
But then, okay, so you should understand, almost all the energy in the vacuum is in electromagnetic waves. However, there are virtual particles, protons, neutrons, uranium, small dogs, they're all in there. So you would, if you had a sufficiently accurate experiment, the electromagnetic, let's say you use 2 pieces of glass. The electromagnetic waves, they could reach through the glass, but the dogs wouldn't fit. And if you did it precisely enough, you would see the Casimir effect because they're dogs bouncing around on the outside, but not in the.
Right. But as you know, if you take a couple pieces of glass that are smooth enough, close to each other, they will be attracted
They
and
will
they will
stick
bond.
together.
Yeah.
Right. I don't know if you've seen this. This is they make draftspeople used to have ivory blocks. They were reference blocks that every draftsperson used for scale models, no longer used because of computer drafting tools. But my father had a pair of these blocks, and if you, 2 ivory blocks, they were so smooth, if you rubbed them together a little bit, you couldn't get them apart this way. You had to slide them apart because the bonds, the electric bonds between the molecules,
Van der Waals forces, that's right.
Van der Waals forces. So you could postulate a different model for what goes on between the plates. The plates are not touching.
Right, but there's still Van der Waals forces
There are
that they can feel
forces there.
if they're really close.
I think that the way to think about it is people have given up trying other things because this works.
Well, that's not a good reason.
I know. And somewhere,
That's terrible science.
I know, somewhere one of you, when you do a master's thesis, you
Yeah.
could say, I'm going to consider 2 dielectric plates, like glass or plastic, and do a theory. Not this way, because this assumes that the plates are metallic and not touching. I could do a theory based on a different approach and see what you get for the forces, and then do the measurement, and so you perhaps could get the same thing, except it wouldn't be 8 to the 4th, it would be
Right.
8 to the 15th,
That's what I'm
and
assuming.
different parameters.
That's what I'm assuming, is that it would be a different proportion.
We have to keep poking at this. Okay, I think we're done for today.
Thank you, Ed.
Thanks. I sent you something